enough to make a black hole. And that's exactly what people predicted, the black hole theorists. And that is exactly what we actually see in nature sometimes. And that's how we get black holes to begin with. But the uncompressing thing that you're asking about, that would be to say that a star, it's dead, it's made a black hole. Can you now rekindle it? I don't know about rekindling a black hole. I think that would be hard, but we can talk about how sometimes some things may happen with white dwarfs that lead to certain more energetic situations in the form of a nova. So we can talk about that in a bit, or maybe another day, because today I want to continue with the black holes. But great question though. I'm going to keep it in mind to talk about nova again. Somebody had asked about that anyways in the previous live. Okay, so as you might know, the second law of thermodynamics basically talks about entropy and how entropy always increases. So this is something of importance in this particular discussion that we're having today about the black holes and how thermodynamics may play a role with this insight with the black holes. So this whole concept of the black holes, basically things are going in, nothing is coming out, would kind of lead one to believe that you're losing the information in some way. But is that really the case? That's what is being probed here by Stephen Hawking and others. So let's read here. The second law of thermodynamics has a rather different status than that of other laws of science. So by the way, the second law of thermodynamics, which is that entropy always increases, entropy in a system always increases, is by the way, a lot of people's favorite law. But it's not the same exact kind of law as some of these, some other laws that we may talk about, like Newtonian laws. So let's see. So it's not quite the same as some other laws of science, such as Newton's law of gravity, for example, because it does not hold always, just in the vast majority of cases. So it is a lot of people's favorite law, but it only holds in the vast majority of cases, not necessarily always. The probability of all the gas molecules in our first box. So we had talked about a box and having gas molecules in it and what sort of configuration of these configuration those would take in the box. The probability of all the gas molecules in our first box being found in one half of the box at a later time is many millions of millions to one, but it can happen. So basically we're saying that entropy of a system generally increases. So if the gas molecules all sort of arranged themselves very perfectly to one corner or something like that, that would be quite improbable, but I suppose it could happen. It's a very small chance, but it could happen. Just in the vast majority of cases, probably not. So that's what he means here. However, if one has a black hole around, there seems to be a rather easier way of violating the second law. So violating the second law in the case of the gas molecules by saying that, oh, maybe the gas molecules, there is a little chance, very small though, that the gas molecules will arrange themselves in a very tidy manner. The chance is very small, but it could happen. But what about with a black hole? Once there is a black hole, it seems like we're sort of maybe violating this second law. Just throw some matter with a lot of entropy, such as a box of gas, down the black hole. The total entropy of matter outside the black hole would go down. One could, of course, still say that the total entropy, including the entropy inside the black hole, has not gone down. But since there is no way to look inside the black hole, we cannot see how much entropy the matter inside it has. So it is basically sort of to the point of asking, to the point of somebody, when somebody asked about, it's only eating things, it's only kind of swallowing things in, but what about something coming out, such as the information about the entropy that we just did something about, right? If we just throw a bunch of gas, like a box of gases, into the black hole and it swallows it, we now don't really have information about what happens with the entropy. Is it true that now that information is lost forever? Is it sort of a violation of the second law of thermodynamics? What is up with that?